Welcome to Quantum Curious, and in today's video, I'm going to discuss squeezing in spin variables of atoms. The previous lectures, we studied that how can we generate a squeeze state of light, and we saw that we can generate by reducing fluctuations in one quadrature and increasing fluctuations in the conjugate quadrature to saturate the Heisenberg uncertainty relation. So our focus in the previous lectures related to squeezing was on the bosonic operators and the bosonic field. So in today's video, we are going to discuss a different set of system, and you can say it is a fermionic system, and we will see that how squeezing can be generated in these kind of systems and how is it different from the squeezing in bosonic system. So first, I will go through the introduction of spin, what is spin of the electron, and then I will discuss how can we generate squeeze states of atomic spin variables in a two-level atom. Then I will discuss that how can we generate spin squeezing in a multi-atom system. So this is going to be very interesting. So let's start with the introduction. So we know that fundamental particles like electron have intrinsic property called spin, and it is like you can see in this picture as the electron as a spinning top or a spinning ball, and the axis around which it is spinning, it is regarded as the spin axis, and it is showing the direction of spin. So we know that electrons have electric charge, and we know that anything having electric charge and spinning produces a dipole moment, and this dipole moment interacts with the electric field and magnetic field. So that is how we define spin in classical physics, but we have analog of this in quantum physics. And but this property of spin in or dipole moment in uh, quantum mechanics is quite different from what we study in classical physics. So we have a spin and it may have three components, and these three components follow this commutation relation. And this is quite different from what we studied for the bosonic system. And the uncertain relation that these three components are going to follow will be like this, and it is quite different from the uncertainty relation for the quadrature operators, and we will see that how it is going to be uh, different when we will consider the squeezing of spin variables in uh, in two-level atom and multi-atom systems. So let's move on to the squeeze states of spin variables in single atom. So in order to get squeezing in one of the spin component or the fluctuation or the uh, squeezing in the fluctuations of the one of the spin component, uh, we have to reduce it, uh, and this reduction will give us this inequality, and this quantity in at the right hand side of this inequality is a standard quantum limit in spin squeezing, uh, and we have to achieve this in order to get reduced fluctuations in one of the uh, quadrature fluctuations. So you could see that a spin squeeze state uh, atom, and we have mean, or you can say spin in the z direction, and we have a cloud of fluctuations in the x and y directions. And these are quantum fluctuations, and these arises due to the uncertainty relation. And you could see that here we are representing spin squeezing with an ellipse. So you could see that there is increased fluctuations in the y component of spin, and we have reduced fluctuations in the x component of spin, x component of spin. So we have spin squeezing in the x direction of spin. So this spin squeezing can be represented by a squeezing parameter, and this is the parameter showing the uh, showing the squeezing in the ith component of the spin. So in order to in order to have a spin squeezing in ith component of spin, we have we must have this parameter less than 1. And for maximal squeezing, this has to be 0. So let's study the fluctuations of the spin operators in two-level atom, and we will consider the case for the fluctuations in the x component of spin. So we can write x component of spin in terms of spin up and spin down operators. And these two operators work as a annihilation and accretion operators in the bosonic field. So we can write the variance of x component of spin in this fashion, and let's uh, try to solve this expectation value of the addition of or you can say expectation value of the uh, spin x component squared. So we can expand this term like this, and we know that spin up and spin down operators can be written as this. So if we are going to square them, they are going to give us 0. So we can check this by taking the conjugate, a complex conjugate of the spin operator, and then multiplying with itself, and we can see that it is going to be 0. And uh, these two terms, the addition of these two terms is going to be 1, because if we plug in these values, we are going to have uh, the addition of these bases, and we know that this is going to be uh, a completion relation, and we know that it is going to be equal to unitary. So putting this value of this expectation value, that is we have gained as 1 in this, we are uh, come up with another useful expression for the variance or fluctuations of the spin uh, x component. So we can see that if we have non-vanishing dipole moment for a two-level atom, we can have fluctuations below standard quantum limit for this spin x component in two-level atom. So we have to prepare our two-level atom in such a state that we have a non-vanishing dipole moment. So let's try this state. So we have a two-level atom in a superposed state of this kind, and we can see that this superposed state is not a maximal coherent state, as it has uneven probability amplitude. So, but it is in a superposition state. So let's take an example that we have a two-level atom, and it is in spin or it is in a ground state, then the value of this parameter is going to be this pra- the value of this parameter is going to be 0. And if we have a two-level atom in spin up or in excited state, we have again the expectation value of this quantity uh, going to be 0. So we want that the atom should be in a superposed state of the excited and a ground state. So then we have non-vanishing dipole moment. And we could check this by calculating the expectation value of these operators for this state. And uh, the inversion of population operator is going to be 1 by 4. So plugging in these values in these plugging uh, sorry plugging these values in this expression, and then plugging uh, the value of fluctuation or variance of spin x component in this parameter, and also plugging in the value of expectation value of the inversion of population. In this expression, we are going to have this uh, value. So it is strictly less than 1. So we have a fluctuation in x component of spin, or we have squeezing in the fluctuation of the x component of spin. So we have achieved this through the superposed state uh, of ground and excited state in a two-level atom. So let's see what happens when we have uh, maximal coherence in the ground and excited state. Then we have dipole moment as 1/2, but the inversion operator is going to be 0. And then this parameter becomes uh, indefinite and undefined. So the maximal coherence does not lead to a maximal fusion. So we can actually see this as there will be no oscillations of the electron uh, from the point of view of an observer. Then there will be no dipole moment, and then there would be no dipole moment, so there will be no squeezing. Or you can see in other ways that this state has equal uncertainty, and this uncertainty is already equal to the standard quantum limit. Then we uh, could not restrict or could not uh, take it down below the standard quantum limit. Then we would have no squeezing in spin variables. But on the other hand, this state can be thought of as unequal uncertainty in the spin variables. Then we can uh, have some squeezing in the fluctuations of spin variables. So let's move on to this multi-atom system. So consider we have a multi-atom system, and it could be n atoms, and we can have spin up and spin down operator as the addition or summation of the individual spin up and spin down operators, and the inversion operator can be written similarly. And then we have uh, variance of spin x component written as this. So by looking at this expression, we can see that either we can generate spin squeezed state uh, with the help of non-vanishing dipole moment, and similarly we can also generate spin squeeze state by uh, two photon collisions. So let's see the example or the important statement of spin squeezing. So a system with the variance reduced below the standard quantum limit in one direction, normal to the mean spin direction, is called spin squeezed. So in order to define spin squeezing parameter in multi-atom system, we are going to use this expression. So consider we have a number of atoms, let's say n number of atoms, and we align this, the spin of these parameters or these atoms uh, to one axis. And then we have uh, mean spins on the axis orthogonal to this axis will be going to be 0. So there could not be spin squeezing in individual atom, but there is chance of squeezing in uh, in the in the in the atoms collectively. And this is the idea of spin squeezing in multi-atom system. So you can see that there is a cloud of uncertainty or fluctuations orthogonal to the mean spin direction. So collectively, there could be squeezing in the in these spin components orthogonal to the mean spin direction, but there could not be any fluctuations in the individual uh, spin components orthogonal to the mean spin direction. So this is the idea of the collective spin squeezing in the atoms. So this idea has many applications as it could be used as a measure of entanglement. So if we can observe some kind of squeezing in collective spin, so we can say that there is an entanglement in the atoms that we have generated or that we have aligned. So this idea could be used for quantum metrology and enhanced precision measurements. And there could be open possibilities or applications of open possibilities or uh, open possibilities in applications like in the field of quantum information processing and quantum computation. So in this lecture, we studied that how can we generate spin squeezing in multi-atom and single atom, and we saw that how it is different from the squeezing in bosonic field. And we saw that the squeezing depends upon the state of the atom rather than uh, some intrinsic or you can say other properties of the field. So this is for today. If you like this video, kindly subscribe to the channel. And if you have some suggestion of improvement of my content or any kind of complaint or suggestions for the content uh, or the curriculum that I'm using, kindly do comment below. Thank you.